So we will probably be discussing the first 6 problems today, the last problem, and maybe the last problem from May cook-off will be discussed together so that they can be discussed at more depth than time will permit today. Hopefully my voice is clear. Okay. So let's start the problems one by one. We will go in order of difficulty. So the most solved problem, lost weekends, right? So this was the cakewalk problem of the round. I think the problem statement can be briefed in the following way. There are like you are given some task, and every day you are given allotted some amount of task, and you have to say that whether you can do it in 5 days or not. It's framed in another way that you have to work in the weekend or not, but effectively you can reduce it to whether you can complete it in a total of 5 days or not. So the answer is actually pretty simple for this. I mean, okay, so there's also another factor of P. So it states that if you do 1 hour of work at office, it is equivalent to P hours of work done at home. This should not affect much of the question because like if you are allotted 10 hours of work at your office and P is let's say 3, then you can just say ki I have to work 30 hours at home and then just do your calculations according to that. Right. So the solution was simply something like you just add all the numbers together and see if it's greater than 24 into 5, something like that, right? So yeah, it's pretty simple. You just have to do a if else checking. Um, most of the people who attempted it solved it, I guess. Yep. So we will move on to the harder problems one by one. Okay, so this problem was this is a this is also pretty simple. You don't need any prerequisite knowledge for solving it. So there are two persons, Alice and Bob. Um, both of them are walking in the positive x direction. It's also given that at the ith second, Alice will have a speed of ai and Bob will have a speed of bi. So what they want is a total of how much distance do Alice and Bob walk together. So they define it as weird distance, but it's basically for how much time do Alice and Bob walk together. So you are given the speeds of Alice and Bob every second, okay, and you have to report the answer. So just to give you a bit of a visual intuition, let's say the distance is so let's draw a graph of distance versus time, right? So y-axis is let's say distance, x-axis is let's say time, and at each second, since Alice and Bob's speeds are given, let's say the yellow line is for Alice, right? So the slopes are basically the velocities, right? Rather the speeds, velocities, whatever. And let's say the red line is for Bob. Okay. I might, okay, I want to make the timings better. So my drawing is not that great, but yeah, something like this. Like this. So yeah, so we effectively have to say what is the distance where this portion is overlapping, right? Red and yellow are overlapping. So note that there might be such intersections possible, but since so it might be that Alice was at some position at let's say the 5th second and Bob was also at some position at the 5th second, and then they somehow crossed the path, but it will be like the total distance they are traveling together is instantaneous, right? It's just at that moment, so it doesn't really add to our answer. So such intersections basically add 0 to our answer, so we can effectively discard them. The what is the main thing that we want to know, when which are the times when Alice and Bob are both at the same position, right? And the speeds for both of them are the same over the next second, correct? So let's say they are at the same position at the fifth second, and both of them have a speed of, let's say, 3 after the fifth second. So what is the distance that you add in your total sum? You just add 3, right? Because you are traveling at a speed of 3 for 1 second, so you basically travel a distance of 3, uh, whatever unit you have. So let's say 3 meter together. So yeah, so whenever you see that Alice and Bob are at the same position, and you see that they have the same speed for the next second, you just add what the speed of Alice and Bob were to your answer, right? um Hopefully that is clear. If there are any questions at any point, feel free to write in the chat. Yeah, so hopefully this was simple also. um yeah, um, so one question might be, what is the distance, because we are given the speed. So remember that we are only considering time intervals of 1 second. So if you have, say, speed of 5 meter per second and you have 1 second, and you are just traveling 5 meters, right? So whatever the speed is, that is the distance you travel in that particular second, right? Let's move on to the third problem then. Okay, so the third problem was slightly trickier. So it's given that there are two strings, A and B, I guess. Both the strings are given. Yep. So there are two strings of length n, and then you can do the following operations. Okay, so what is an operation? You choose a certain subset of the indexes. Let's see with the alphabetically smallest letter among all the chosen indexes for A. Okay, not for B, we are only considering A. And then convert all of the selected indexes to C, right? And in this way, you want to make A equivalent to B, right? So let's take their example, the sample solution that was provided, like the sample test case, and see how that goes. Uh, Hopefully it's visible. So let's say, so obviously here A and B are different, right? I mean, A as in the string A and the string B. Now, how do I approach the problem? So one thing is clear is that you kind of want to know what is the smallest character that I'm going to pick among my indexes, right? So for example, one possible operation here could have been, let's say you chose 1, 3, and 5, right? If you did this operation on A, what will be the string? A, B, A, right? Your string B does not change. So yeah, so this is one possible operation that you can do. What is another possible operation that you can do? You can do 1 and 2. You just take these two indexes and you get a string A, C, A, B, right? So this position effectively changed. Here, this position and this position had changed, right? So this one and this one. So these are two possible operations you can do. So it does not. So how do you go about selecting all these subsets, right? Because you also have to print the subset. So it's not like you can just get some like formula or something, or somehow if you just ensure what is the minimum number of operations, that is not enough. You have to actually pick out all the subsets and print them, right? So yeah, so let's say we fix the thing. So what we usually want to do is, whenever we have something like you pick a subset of things, and then you are doing some operation based on a certain property of that subset. So here, what is the property? It's effectively the smallest number that we have chosen inside the subset, and then we are doing something using the property. In the problem, it's basically like you are replacing every character by that chosen element C, right? um, Yeah. So okay. So one thing I should clarify: I am doing one indexing here. The problem has zero indexing. So I mean, uh, I think it has zero indexing. So just keep that in mind. Like, yep. So whenever we have this kind of problems where when we choose a subset and we have a property of the subset, that is the most important thing. We want to fix that property that we are talking about. Like it's usually some like smallest element or some function of the subset, something like that. And we want to fix that element and then choose the subsets. So instead of first choosing the subset and then like finding the property, we first fix the property that we say that okay, this if this is the property, what are the valid subsets that I can have, and we go about in that way. So here it makes sense if we try to proceed in that way, that we fix this what is the smallest character that should be there in our subset, right? So let's say we select that in the first iteration the smallest character is a, right? Now we, let's say, choose a subset of indexes, let's say 1 4 and like 1 2 4. I'm just doing it arbitrarily, 1 2 3, such that the smallest character from these is precisely a, right? Because if it's not, then choosing a does not really make sense. So you will have many subsets that are possible, right? I mean, since a is actually the smallest possible value, you can have like all possible subsets. But yeah, now let's say you want to take a subset that you got whose property was a, right? Let's mark this as capital A, or yeah, let's say capital A, and you want to change the indexes at all of the positions that are included in capital A to the character A that we had chosen, right? So for example, in the above string, if we had chosen A to be, okay, there is a bit of a clash in notation. Let's call this X for now. So let's say X is 1, 3, 1 and 3, right? So if we did this operation, we would have got A, B, A, B. And let's say we could have also chosen this subset, right? 1 comma 2, and then we would have got A, C, A, B. Now whatever goal is from here is to kind of greedily choose the indexes so that for all the positions where B was, let's say, A and A wasn't A, like I mean B had that character A at that position and A did not have character A at that position, we want to include all those subsets, right? We want to include all those indexes in our subsets, right? Because all those indexes need to be changed. if if at a certain index A and B are the same, they don't really need to be changed, but if they're different, then that index of A needs to be transformed into that particular index of B. So we can either do this using two subsets, but why use two? We could have just combined everything together, right? We don't have any other clauses that it has to be you have to maintain some gaps, or you can have at most k things in a subset. We don't have those restrictions. So for every position in B, right? So here our particular positions are this one, and okay, so only this position too. So for every position that is in, so I'll just, for the sake of an example, I'll make the string like this. So the positions we want to consider are this and this, right? So for every position of B where it was an A, but that position of the string A wasn't the character A, we include all these positions into my subset, okay? Which I want to like execute when I'm considering the character A, small, like the character A itself, right? So here, for example, I would have chosen 1, 2, not 3, not 4, not 5, 6. And then I convert. So if I make this operation, then whatever needed to be A in string B becomes A in string A as well. So effectively what we have done is for all those positions of B, so what we have done is for, okay, I'll try to explain again from the beginning of it. Uh, yeah, sure. Sorry, the notification did not come. So So okay, so let me just go over what all the chats here. Right, so yeah, it should be 0 index, but I'm doing it 1 indexed. Okay. Uh, so by smallest character, I mean A is the smallest character, and then it's kind of like by ASCII value. So A, B, C, D are the characters in order. So how to choose the index? That's what I was kind of explaining. How to choose the index right now. Like so, how do you choose the index? So let's say we have fixed a character A. So if we fixed the character A, so choose all those indexes. I guess it's called indices, for which B of I, so for which B of I equal to A and A of I does not equal the character A, right? So we choose all these indexes I in our subset X. So X contains all such I's. Okay, so this is for X for character A, kind of. Right, so basically we want to choose something like this. If we fix a character A, we choose a subset called X of A, which contains all those I's which satisfy that B of I is equal to A and A of I does not equal to A, right? And okay, now we can, so after this operation is done, is done, so in our example string, so yeah, so I should have named this P and Q, otherwise like A, B, everything is confusing. So let's just call the strings P and Q. So after this is done, what happens is everywhere where Q of I was A, P of I equal to Q of I, right? I mean, other parts can be also equal, but after the first operation, at least what we have confirmed is at least that all the A's are kind of set in position. So all the A's are set in position. Now the A's are done, right? So let's try to fix another character, let's say B. Okay, so after A is done, let's fix for X of B, right? So for B, what do we have to do? Note that we cannot include any position in A that contains in any position in P, right, which contains an A. Okay, so this cannot include any position in P such that P of I is equal to A. Correct? I mean, if it were to include such positions, then the smallest character is actually A, right? It's not B. But we are like X of B is kind of defined as the smallest character needs to be B. Fine. So that is how we select X of B. Now, again, in the same procedure, where everywhere where Q of B, so X of B kind of contains I if Q of I equal to B, but sorry, P of I does not equal to B, right? It's very similar to how we had chosen X of A, right? And we kind of continued doing this for every character, right? So one possible problem here is, so these two sentences kind of I mean might contradict, right? Like X of B cannot include any position where P is A, right? And then X of I must also contain all positions where P of I not equal to B. So what if Q of I was equal to B and P of I was equal to A, right? I mean, this kind of suggests that it should be in the set by the definition of XB, but it also suggests, like, again, XB cannot really have this ith character, right? Because If it does, then B is not the smallest like character inside the set X. That is how we defined X, correct? So yeah, so this kind of leads to a contradiction, right? So whenever you have such a contradiction, that means the answer is not possible, correct? Okay, so what will happen if we change a letter which we would need later? Let's say P of A, B, C, A, and Q was A, A, B, A. Right. So how you actually want to implement this finally is you want to probably go from top to bottom, right? So you first want to set all the Z and then go down one by one. Then these problems will probably not be happening, right? So yeah, so you actually have to kind of start from the highest ASCII value and then go down. But here I am kind of, I mean, I would have mentioned that at the end. So this was one of the point I wanted to mention. Yeah. Yeah. Okay. So anyway, as I was saying, if a contradiction like this happens, that P of I, so what is, so we use the examples of A and B here, correct? So what if P of I, so I mean, this kind of extends to anything where P of I is less than Q of I. Then you cannot really ever set P of I to Q of I, correct? How you can like prove this more, like it should be intuitively clear. I mean, I showed how the example with only the characters A and B, but you can generalize it very easily for A, B, C up to X, Z, sorry. So if at any position you find that P of I is less than Q of I, well, less than is like compared by the ASCII value, then just answer -1. Else just try to generate these sets of X from the higher value to the lower value, actually, like when you are actually implementing the algorithm. And that's about it. So one other thing, one other edge case that might happen is Q might contain some character. Let's say Q is A, C, A, and B is, sorry, P is A, B, A. Then you cannot ever get the character C in A, right? You like, it's not possible. So this is also another edge case where if Q contains a character which E does not, then just report -1. So yeah, so these were the two edge cases, and otherwise it's, I think, simple to find the sets of X for every character, right? So hopefully all the doubts have been cleared. Are you like, hopefully you're able to understand the problem and the solution as well. So tree difference. So let's see. So in this problem, you are given a tree with n nodes. You are also given a value associated with each node, and you are given q queries q queries that you have to answer. So for every query, you are given two nodes A and B. Um, let S be the set of all nodes on the simple path uh, from A to B, and find the minimum value of ax minus ay for all pairs x and y that belong to S, right? And when we see the constraint, the most like glaring fact is kind of ai is less than equal to 100. So usually, I mean, if it wasn't important, then it wouldn't have been given, right? So whenever you see some unusual constraint like this, I mean, usually setters like to set constraint up to 10 to the power 5, 10 to the power 9, things like that. So whenever you see a very small constraint like this, uh, you can kind of guess that this is important, right? uh, yeah. So let's try to attempt the problem. um, let me draw a tree. So So I'll just draw a single path. There can be other attached subtrees, some parents and such, but oops. Sorry. Yeah, so these are, let's say, the edges in the path. and then this will have a parent, and there might be some other children down here. There might be some other children down here, but let's not worry about those at the moment. So let's say that this node was given as A in our particular query, and this node was given as B in our particular query, right? So I'll just open the chat here once. For the codes of the all the problems, please like see the editorial. I'll probably be discussing the codes for this, the next, and the third, like for the problems after this. But for the easier problems, if you want to see the code, they are like the setter code, tester code, editorialist code, all are mentioned in the editorial. So hopefully you can check it out from there. So right. So let's see what the first subtask was. So the first subtask was just nq less than equal to 1000, right? So that kind of suggests that we can do a n into q times algorithm. So it's a bit of a brute force type-ish thing, right? So let us set some values for the example. Let's say this is okay. I'll just make font a bit smaller. So let's say the value is here 6. Here is, let's say, 10. Let's see what all values do we want to give. 5, 14, 11, because why not? Then there is, let's say, 20. And let's give this a value of 2. Let's give this a value of 27, right? So these are kind of the values, like hopefully you can see it, like B's value is 27, the value here is 10. Sorry for the bad drawing. So what is the, so we have to find the minimum separation between two values, right? So what is the crudest way that we can do it? The most like brute forcey way. We can travel from A all the way up to the LCA and then down to B, correct? And then we can put all the values in a multi-set. So note that you don't want to use a set kind of, like, again, I mean, this is not close to the original solution probably, but still don't use a set, because like there can be colliding values. So let's say we collected all these values into an array or vector or anything of that sort, whatever you want. So let's say the values are 6, 10, 14, 5, 11, 20 to 27. These are the values, right? You collected them somewhere, and then you'd kind of do a pairwise brute force. So you check with 6 with 10, 6 with 14, 6 with 5, and like you check every pair of numbers, and then just take what is the minimum separation. So just take minimum of mod x minus y, correct? What is a better way? If you could have just sorted all these values, so if you sorted all of them, um, then it would have been like 2, 6, sorry, 2, 5, 6, 10, 11, 14, 20, 27, right? So this is a sorted array. So a nice property in the sorted array is like the minimum difference that you are trying to achieve, mod x minus mod y, sorry, I mean x minus y whole mod is minimized. That you can just check the consecutive values and the answer will be one of the kind of like one of the separations, right? I mean, it like if the answer cannot be something like 10 minus 14 or something like that, because if it were, then if there is something in the middle, then you can just reduce your answer by taking that middle element first, kind of, right? So that is kind of the solution that you want to have. So what is the complexity here? For every query, you kind of traverse the whole path, right? So for every query, so you traverse the whole path. That might take a time of n, correct? And then you are effectively sorting all the values. So is it n log n? Yeah. So something like this. Now, the sorting portion, you can actually make it more efficient since there are only 100 values. There is something called bucket sort. So bucket sort means you keep a frequency array. So let's say 0, 1, 2, 3 up to 100. And then every time you get a value of, let's say, x, you make the xth position as +1, right? So you are kind of making buckets where each bucket represents a particular value, and you put your element into the respective bucket, and then after putting everything into their respective buckets, you just traverse the buckets in order. So for 0, 1, 2, 3, 4, up, so on and so forth. So what is the time that such an algorithm will take? It will take exactly the time uh, n plus Maxwell. Okay, so Maxwell here is exactly 100, so it's much smaller than n log n, obviously. But the complexity is still q into n, and this was sufficient to pass subtask 1. Correct? Subtask 2 is a very slight modification of this, and it involves something called the pigeonhole principle. So what is a pigeonhole principle? The statement is very simple. If there are like n holes, so let's say there are n holes like this, okay, and there are n plus 1 pigeons, okay. I will not even attempt to draw any pigeon. So if there are n plus 1 pigeons and there are n holes, and each pigeon wants to go into one of the holes, then there will be at least one hole with more than one pigeon. So if you kind of have 4 holes and 5 pigeons, then at least one of the holes will have more than one pigeon, right? I mean, it's kind of very intuitive, and obviously, I mean, it's very obvious, right? But it's useful in a lot of problems. There are stronger versions of the pigeonhole principle. So a stronger version of the pigeonhole principle is something like if there are k buckets, rather k holes, and k holes and x into k plus 1 pigeons, then in at least one hole there will be more than x pigeons, right? So this is a bit stronger of a statement than the like n holes and n plus 1 pigeons, but yeah. So how is the pigeonhole principle applicable here? So notice that we have only 100 values, correct? The values can be from 1 to 100, but we have, let's say, 200 nodes on our path, or like we can have n nodes on our path, but let's say there are 200 nodes in our path. Then we can safely say that at least 2 of the nodes will have a same value, right? I mean, whatever the distribution of values is, at least 2 of the nodes will have the same value. And whenever we have 2 nodes of the same value, the formula ax minus ay whole mod becomes 0, and you cannot really go down below 0, right, for a modulus value. So that is the minimum value that you can ever, like the best minimum value that you can hope to achieve. So the observation is kind of, if you have even anything more than 100 nodes on the path, you can just blindly say that the answer will be 0. There will be at least 2 nodes that contains the same value, so just output 0. All right, and then if there are more nodes than, sorry, if there are lesser number of nodes than 100, then you can just traverse the entire path, right? I mean, you just go up to the LCA, you again go up along this path up to the LCA, collect all the values in let's say a vector or something, and then do this bucket sort and just compute the value as you would have done in the subtask 1, right? So yeah, you don't really need to do anything different than subtask 1 here. So the only line of code that kind of gets added is the distance thing, right? So how to implement this? There can be multiple ways to implement this. I think the setter and tester codes have some LCA function where you find the distance of the path, and then based on that you can first directly say whether the answer is 0 or not, and then if the distance is less than 100, you traverse the entire path. To me, I think a simpler solution would be something like, uh, so first in a DFS, compute all the depths of the node, right? This is just a simple DFS. Now in subtask 1, what you could have done is, how you could have implemented traversing the whole path is, you have this nodes A and B, right? So some pseudocode will be something like, okay, I'll just check this. So some pseudocode will be like, while traversing the path, you have depth of node, which means distance from node to root. Fine. And how do you get the entire path? Let's say for the moment that you do not know what your LCA is. Okay. So I am kind of entirely trying to bypass the calculations of LCA, because like you need sparse tables and stuff like that for calculation of LCA. So what you can just do is, let's say your points are A and B. So, and you also have a parent array. So parent of node is just, well, the parent of the so yeah, and you are given A and B. So do this while A not equal to B. Let's say if depth of A is greater than depth of B, then I want to move the pointer from A to its parent of A. Okay. So what I do is, so I have this initial vector of, so let's say a list equal to list of all the nodes in the path, right? So I just do list dot insert val of, let's say, parent of A, and I set A equal to parent of A. Okay. And if not, I kind of do the same thing for B. So just include the this and just go up the B ladder. Now what will happen is, basically, so when a certain node is deeper than the other node, uh, you just climb its parent, and same thing for the other, you will just climb its parent. So now how do you ascertain that you will always end at the LCA? Well, when you get to the LCA, note that kind of how both the pointers will reach the LCA at the same time, right? Because if one of them was low, like had more depth, that would have been preferentially gone up the parent pointer. So when they are kind of going to the LCA, so just before they reach the LCA, the parent pointers will be at, like, so this will be a parent pointer, this will be a parent pointer. Now one of them will go up, so it will point to this, and then the other parent pointer will also go up, right? But see, here we have this condition A not equal to B. So when both of them are at the same location, then obviously A equal to B. So it kind of breaks out of the loop. So just keep in mind here that you don't want to include the same element twice in your list, right? So in this form of the pseudocode, you will probably put the LCA twice. Just keep a condition to check that you are not doing that, right? Now this was a simple code for subtask 1. For subtask 2, even you don't even need to calculate the LCA. What you just do is continue doing this loop. If the size of the list, if list.size is greater than like 100, then you just say that, okay, print 0. So in this way, you just use the loop itself. You don't need to calculate LCAs or anything like that. Just go up, go up, go up. When you have seen that you have gone up more than 100 times, that means your path length is total greater than 100. Just skip out of it. So that was the solution for tree difference. So hopefully you guys won't have any problem coding it. So yeah, so one question is how to solve this for AI less than equal to 1E5. There was, I think, a problem that asked exactly this, like it had a higher, like I don't really remember the problem, but it was, I think it was given in the editorial section. Probably I was going through the comments and I think it was there. But yeah, so this solution does not work for larger AIs, right? Because the complexity of the solution is what? Finally, you are just doing Maxwell number of operations, right? You are going up 100 times at most and then doing a bucket sort of 100 elements. So this was the expected complexity. So yeah, so LCA is not enough. As I showed in the pseudocode here, you don't really need to do LCA. You just start climbing parent pointers from the deeper node. That will, you will always end at the LCA, but if you kind of exceed 100 nodes, then just print 0, since yeah. So, right. So any queries for this problem? Right. So, okay. So the fourth problem done. So yeah, the idea was very simple. Just apply pigeonhole principle after the first subtask. So yeah, the first subtask around 350 people solved. The pigeonhole principle idea was the difficult part, but yeah. And finally, let's go to the last problem of division 2, escape 1. Right. So this is again a simple problem if you are able to reduce it to what it actually is, right? So seeing this, like you are doing operations, tell them what is the minimum number of operations that you can do. In all these types of problems, it's very critical that you are able to reduce each operation into what it actually is, kind of like. The problem statement is usually given in a different way than, and the reduction can usually help it become more like you can actually understand what is internally happening. So I mean, I'll explain what I mean just in just a moment. Let's say, so the problem was something like you are given a binary string of ones and zeros. You can move a certain one to its adjacent positions, and your goal is so that at the end there is no element whose value is one, right? And the length of the array is 10 to the power 6, but let's not be too bothered about that at the moment. Um, for n equal to 1000, okay, so okay, let's get into the problem. I'll show how to do the first subtask as well as the second subtask after we have like reduced the problem a bit. Let's say these are the position. Okay, I'll draw it in a kind of a circular table kind of a format. So let's say this is 1, 0, 1. Right. So these are kind of this is a circular thing, right? So what is an operation? The operation is effectively something like you are basically making this a 0, and let's say moving this 1 to this position. So this becomes a 1, right? And then you can do again delete this one and move it here. So you're kind of like moving this once around. So how I kind of viewed the problem after I draw this diagram is you're taking this one and you're moving it to some other place, right? And adding it to some other value. Okay. So what happens when you add it to some other value? This one becomes a 0, right? This becomes a 2. So in some sense, you are kind of eliminating the need of moving this element at all. So using one movement, you are kind of destroying in some sense two ones. Okay. So two destroyed kind of. Okay. So yeah, so using one move, you are kind of destroying two ones. Okay, so what is the effective goal here? You want to destroy all the ones, correct? So this statement might not be always true, right? I mean, so what is the most obvious thing that I could think of? I can say that okay, for every one, go like transport it to the one to its left, right? And let's say for this one, we are transporting it back here. Or we could have done it the opposite way. We could have transferred it. Uh, we could have transported this to here, and then this to here, right? I mean, these are the two very obvious things that we could have done, right? So let's keep this in mind for 1 second. Let's just get over the base cases, like the edge cases kind of. So it's obvious, right, that if the string contains all zeros, we don't need to do any operations. There are no ones. If there is exactly one occurrence of a one, then we cannot really do anything, right? Because we cannot combine it with another one to make it a two. So it's not really useful, correct? So these were the two base cases if there is no ones or if there is exactly one position of one. Okay. So let's make some more observations. There, if once an element becomes two, the best thing that I want to do maybe is like mix it with another one. Okay, so let me write it down. Once a element becomes two, we want to mix it with a one. So we don't want to mix it with a two, right? Because that will be just a waste of an like multiple operations, right? So one thing I should make it clear: this transportation isn't one operation. It's actually the number of edges that you visit. Those are the number of operations that you are making during one transportation. So keep that in the back of your mind, because in the problem, one operation is shifting once. You're shifting here 3 times, so it takes 3. The cost is 3, right? So yeah, so we don't want to mix it with another 2 or really any other number. We are just concerned with mixing it with 1. This is the first observation, kind of like these are like kind of obvious once you think about it. Second is, instead of moving 2's, we can only just move 1's, correct? Like whether you take A to B or B to A, it doesn't really make a difference. I mean, traveling clockwise and traveling anti-clockwise has the same cost. It's just a number of edges that you are covering. So just don't think about mixing, like moving the 2's at all. Just think about moving the 1's. Okay, so with these out of the way. So what all can we observe? So what all more? So the most obvious thing that should come to your mind is take everything to the right, right? I mean, take everyone to the one that is to the right of it. And you might think that that might be minimizing the cost. But in actuality, it might not be the case, right? Because what can happen is you can take this one here, and let's say just for the sake of the argument, okay, I deleted those observations. Oops. Sorry, like hopefully they were like intuitive enough, so they aren't really too much of a trouble. So let's say this was also 1, right? And this was a 1, this was a 1, this was a 1, this was a 1. So what we can do instead is take this here, take this here as well, and let's say take it here, right? So we are not just moving to our immediate right neighbor, we can also kind of mix them up and they might give us a better solution, right? Okay, so yeah, correct. Now so one more thing that you might try to think is you want to go to the closest neighbor, correct? So you might want to take this to here, this to here, since these are the closest neighbor. For this, however, there is a choice. You might take it here, you might take it here, and it's not kind of obvious how you want to break ties, correct? Because again, like if you are trying to do it in a sequential order, like taking a 1 there, taking a 1 there, then what might happen is, let's say you processed this one first, right? And you took it here. Then and let's say there was a 1 here as well. Then you processed this one. You took it here. Like let's say you're randomly choosing. Now for this person, you don't know whether you want to go here or whether you want to go here, right? And I mean, you cannot really go either way because the distance just increased. It's now a 0. This is now a 0. This is also now a 0. So choosing blindly is kind of bad because you could have then either chosen to go here, and this would have been a better choice. So you would have, so one like kind of accompanying observation here is you kind of want to keep everything towards the middle. So you want to shift everything towards whatever the middle one was. So so yeah. So another thing that comes from these observations is that what are you effectively doing? You are just basically grouping together things, right? So you are making this group, you are making this group, and you are kind of making these groups where all the ones merge towards the one that is at the middle. So if there are like 3 ones here, you want to merge them in the middle, like towards the middle element. And let's say if there was 4 ones, so this is another important observation that follows from here. So let's say there are 4 ones like this, 4 nodes, and you want to group them together, right? So let's say that you want to bring everything towards this position. So instead of taking all these, so let's say this you put it here, but instead of also covering this here, a better choice would have been just take it here. Then this one would have been destroyed. This one would have been destroyed, right? Similarly, both of these have been destroyed. So that also does your job, and it takes lower number of transfers, right? So I think again I should make a clarification. When I say a transfer, I mean shifting one edge. When I say a transportation, I mean kind of doing multiple transfers to go to another location. So um, hopefully these are like clear. I mean, it makes sense. So yeah. So I mean, the why this is I'm saying all this is this particular move might take 3 operations in of itself. So it's not like this is exactly one operation. This might take more than one operations. Correct? Right. So what is the kind of key insight that we gain from here? So if there is something that has a large size, we can probably break it down further, right? So if there were more ones, 5, let's say there were 5, okay, this is also critical case. If there were 5 such positions, what we could have done is, so one thing that you might think of, okay, let's group them into pairs of 2. I mean, then this would have been lonely, right? So you kind of want to group it into one of them also. So the basic thing that you kind of want to do is you either have groups of 3 and groups of 2. Okay, if you have a group of 4 or bigger, so if there are more than 3 elements, if there are more than 3 elements, you can definitely like break it up into 2 groups of 2 and 3, right? Okay, so we have reduced our problem a lot till now. We have like gone to the point that we can now safely say that we effectively want to group the ones together into groups of 2 and 3, and then kind of calculate what is the cost of transporting. So in a group of 2, you are basically transporting A to B or B to A, doesn't matter. For a group of 3, when there are A, B, C, you are transporting A to B and C to B. So everything towards the middle element. And what are the costs? So for example, in this example, this transportation would have taken a cost of 2, this would have taken a cost of 2, and these would have taken a cost of 1s, right? Again, note that it's just a number of edges that we are traversing. So the total cost here would have been 1 plus 1 plus 2 plus 2, 6, right? So correct. So till now we have reduced our problem by a lot. Let's see what we can do more. So a general strategy, a very general strategy in problems that involve cycles, so like like circular arrays and stuff like that, what we often want to do is, like, obviously linear chains are easier to handle, right? You don't have to worry about going past one end and back into the other, right? Linear chains facilitate DP better, correct? So what we often think about when we look at circular problems like circular arrays, stuff like that, we say that, okay, let's say our chain breaks here. I mean, there will obviously be an edge somewhere which is not covered by a group, right? I mean, if there are only like, even if there are like 3 edges only, 3 nodes only, if there are 3 nodes only, we only take, like if there are k ones here, we take k minus 1 edges, right? So one of the edges will be free. You can break at that edge and still not affect your optimal solution. So whatever your optimal solution was, it had one of these breakages. So subtask 1, how we would have done is, we say that, okay, let's say this is the breakage. Now arrange this in the form of just a linear array, correct? And then find what is the best grouping of ones and zeros that you can do. You get an answer, right? Now keep that somewhere. Now you again break this edge. Now again you have a array like this. Calculate the best answer for this array. Take the minimum value of the two answers that you have got and store it somewhere. Then you can break this edge. Again you have a certain array like this, right? Calculate the answer here, update the min, and so on. So you can break at like n places, right? There are n edges, so you can break at any of the n edge. And then let's say we can calculate the correct answer more or less fast, like in a linear pass. So what is the complexity of such a solution? Well, there are n edges. You, let's say, take order n time. Just for the sake of it, I haven't shown how to do it. Let's say you take order n time to calculate the best grouping of neighboring nodes. So it takes an overall complexity of n square. That is enough to pass subtask 1, right? So let's quickly jump into how we can actually group these together. So let's say after we have broken this edge, some edge, now we have a straight array, right? So it's something like this. What I want you to do is, between each pair of consecutive ones, right? So this one and this one, or this one and this one, there is a certain distance that you have to traverse, correct? So for the first pair, you have to traverse a distance of 0, like both are consecutive, or rather, actually you have to traverse a distance of 1 because there's exactly one edge between them. For this pair and this pair, you have to traverse a distance of 2. For the next 3, for the next 3, for the next 3, for the next 3, for the next 2, for the next 4, right? Make sense? So this is actually 4 edges, right? Because it would have been something like this. So yeah. So you kind of have these distances. Now, what does a grouping do when you look at it from a distance point of view? What it effectively does is, it's when you, let's say, combine these 3 elements, you are effectively traversing these 2 groups. Like, I mean, you are effectively traversing this total distance, 1 plus 2, right? Does that make sense? When you are focusing on this group and you are saying that, okay, I want this as a group, that means you are traversing these 2 values, correct? Now, let's say you don't want to group this as such. You say that you make a group here, so you are only basically traversing this value, and then you are grouping these 2 elements together. So what is the total value that you are traversing? You are only traversing the, you are kind of ignoring this value 2, right? This 2 was the distance from the 2 was the distance between these 2 ones. So we are not grouping them together, so we don't need to cover that distance. We need to cover this distance, right? This distance is basically this one. So what are we effectively kind of doing? We are kind of, so let's assume for a moment that we have firstly taken all of the distances together. So diagrammatically, how this would work is, the distances in the diagram are kind of like this. So each orange line that I will draw will have a certain distance, rather red line, let's say. The distance. Now, if you have grouped them like, so what you are effectively trying to do is, you are saying that, okay, I want to discard this distance because I am not going to travel it. I am also going to, let's say, discard this distance that I'm not going to travel, So what are the distances that you do travel? This one and these 2, right? So when you're grouping, it's effectively which distances are you willing to travel, right? So instead of kind of choosing the distances, a better way might be first take all the distances and then discard some of the larger distances that you don't want to travel by, right? Okay. So the most immediate kind of thing that you might think is, we just want to discard the largest distances. Okay, so since we are trying to discard, the total sum of discarded elements should be as maximum as possible to minimize the traveled distance. You might think that greedily just pick up the largest distance and discard it. That is not the best case scenario, and it's evident from this example itself. If you discard this distance 4, so if you say that you are not going to travel all these edges, how will you group this one? You cannot keep it separately, right? And it doesn't make sense to group this one with something that is not adjacent to it. So and like you cannot just leave it alone, right? You have to group it somewhere. So just taking the largest distance might not be the best case scenario. This is the kind of the example why it might not be the best case scenario. So how do we do it? We do it via dynamic programming, because well, whenever greedy kind of fails, you tend to look towards dynamic programming, because dynamic programming kind of assumes all solutions might exist and then chooses one, the best from them, right? So greedily, this won't work. What kind of a dynamic programming might you think of? Let's say, uh, okay, actually what I will suggest is forget about this, okay? Let's just talk about these adjacent distances. I mean, it will be easier. Why? So what is the condition that one cannot be grouped alone? The condition is that you cannot discard both this distance and this distance, right? So in effect, you cannot choose two distances consecutively. Make sense? If you choose two distance to be discarded continuously, then there means there was the one between this two positions, right? So if you discarded both of them and you do not want to travel both of them, that means that one got lonely. It wouldn't have been grouped into anything. So the constraint is you cannot choose two distances that are consecutive. Similarly, you cannot. So there is an edge case where you have to worry about specifically for the first and the last like datas. Um, Probably the best way you can handle it is just add a distance of 10 to the power 18 here, maybe. So in that way you don't have to worry about the first and the last positions explicitly, probably, and you can just enforce the condition that you cannot take uh, you cannot take two elements side by side. So since you're obviously going to take this, then that means you cannot take the 4. Similarly, since you're obviously going to take this, you cannot take this 1 here. So I mean, you can do it. You can separately handle the first and last elements, up to you, right? So the DP, let me go through the setters or editorialist code. That should be, the DP should be helpful to understand from there. So we are just considering the DP part for now. Okay, so we are still considering the solution of subtask 1, right? Right. So this is the code. Oops. Right. So this is, I guess, written in Java, but array list is basically, you can think of it as a vector. In C++, if you are uncomfortable with Java, but yeah. So the DP should be, okay, so the 10 to the power 18, what I meant by that was, what is the constraint that we said is applicable here? You cannot choose two consecutive elements to discard, right? And what is your objective? So objective, choose maximum, choose subset such that sum is maximized, right? Since if you choose a subset whose sum is maximized, since these are the discarded edges that you don't travel finally, When you maximize this set, you are effectively you are minimizing the traveled distance, right? So that is effectively the number of operations that you do. So the thing is, like, you are forced to take the first and the last options, right? You can handle this as is, or you can just say that there is a element of 10 to the power 18 here at the beginning and the ending. So what that forces you to do is effectively you have to choose this. Therefore, you kind of cannot choose this, if that makes sense. So this the ending element kind of has to stay there, which is what we kind of wanted. So yeah. So the DP is hopefully easy to get. So pos.get is effectively the vector notation is something like in C++ you would have just used the bracket operator. Okay, so it's the same thing as this, right? And then you are effectively here what you are doing is you are choosing either this value, and then you have to like forcibly take the one before that. I mean, take or not take. And if you are not taking this, I mean, if you are taking this value, you cannot choose this. And if you are not taking this value, then you may or may not choose the previous value. So that was all there was to it. So I would advise everyone to like actually code this up before seeing the editorial code and everything. Right. So hopefully the DP won't be difficult to understand. Uh, right. So till now, what we were doing, we were splitting at every possible position and then making this array non-cyclic. So non-cyclic, and then we were solving the non-cyclic version, right, using the dynamic programming. What is the file? Like this obviously takes n squared time, right? The next subtask, like the full solution, is very, very similar to this, like this portion of the solution. It only requires one observation. When you're grouping together stuff, so when is a particular splitting not viable? Okay, when you are splitting at a particular edge, when is it bad? When are you not getting the optimal answer from this? When the optimal group would have traversed this split position, right? So again, let's think of it in terms of these separation counts. These were also kind of in a circular position. Okay, so it would have been like 4, and after this you again kind of went. So let me draw this in a nice way. So after this you would have again kind of gone back. Uh, After this you would have again gone back to here. Okay, so imagine that this was also cyclic, right? Because these are the gaps between the consecutive ones, right? So the gaps were cyclic. Now, again, the problem was effectively you can choose any of them to discard, but no two of them can be consecutive, right? Yeah. So when was such a split not good? I mean, actually, there would have been one more element beside this, because when you were splitting here, you are kind of taking the array from this side to this side, right? But there was another edge here that you are actually splitting, kind of the portion where you are splitting. So there would have been another edge value here, let's say x, something like this. Make it like 3, just for the sake of the example. So again, the problem, it was the same problem. You cannot choose two consecutive edges to discard, and then you have to maximize the total cost. Now, when would have this selection, this linearizing been wrong? When optimal group would have been passing over this cutting edge, right? The edge that you had cut, when the optimal group would have passed over this, correct? But the group size can be only 2 or 3. So this group that is passing, it can maybe cover this element, but then what is the maximum amount of thing it can cover? It can at most cover this, right? It cannot really cover this element anymore. I mean, most cases it won't even cover this one only, like the optimal solution. So think we are talking about the optimal solution, in which sections the optimal solution covers. So if so, in effect, what I'm trying to say is, if you are making a split here, here, and here, if you are making a split at 3 consecutive positions, you are guaranteed that one of them will be free in the optimal solution, right? Because we are grouping into at most sizes of 3. Groups of size of 3, you like use 2 such transportation links. They don't use 3. So there would have been a gap somewhere. So the full solution is effectively that you get this circular type of array, and then what you do is you make a cyclic shift. You take one element from the end and put it in the front. That is effectively simulating splitting at the adjacent portion. And then you again compute the solve non-cyclic function. Then you do the shift again, you compute again, and then just take the minimum from all the 3 computations. That was it. Hopefully the last portion was clear. Why we are only concerned about 3 cyclic shifts, because we are guaranteed that the maximum size in the optimal splitting is of size 3. That means it must be using less than or equal to 2 such consecutive edges. That means the third one must be free. I mean, third has to be free, or the second is free. I mean, one of them will give the optimal solution, right? So hopefully this was clear as well. If there are any questions, feel free to ask. I guess not then. Okay, then let's move on to the last problem for today. So that will be absolute min-max. So this was actually a bit harder solving wise than absolute min-max, I guess. At least in division 1, that's what the number of accepted solutions say, but yeah. Okay, so say I make an edge between the 2 ones with maximum distance. After that, how do I decide group all the ones in 2s and 3s? See, you are making an edge between all consecutive ones, right? Now, what I am saying is, you will only traverse some of those edges and you will discard the rest of the edges. Now, how you are selecting which edges to traverse, what I am saying is, assume that you are splitting at one of the edge, which you will definitely not take. Okay, so in the optimal solution, I mean, when I say definitely, I mean in the optimal solution, which you are, assume that you are not going to take it in the optimal solution. Then you get an array, right? You don't have a cyclic array anymore. You have a non-cyclic simple linear array. And then you do a dynamic programming and choose what grouping of 2 and 3 is the best scenario in that array, right? Now, in the subtask 1, what the solution was that you break at every such position. You make an assumption that, okay, this edge is not going to be used. Compute that dynamic programming solution, take the minimum over all the possible values, and that minimum is your optimal. I mean, the optimal solution was one of them, right? And so if you have all of the values, then their minimum is the optimal solution. Now, what the second subtask says is, if the optimal, say when you made the first split, that would have not been the optimal split if and only if the optimal solution had a group which used that particular edge, right? Now what I am saying is, it might use that edge, it might use the next edge, it will not use the edge after the next. I mean, if any among any 3 consecutive edges, there will be at least one edge which the optimal solution does not use, right? Because I mean, you are only making groups of 2 or 3, right? You are making groups of 2 or 3 nodes. For a group of 2 node, you are including one edge. For a group of 3 node, you are including 2 edge. Nowhere are you including 3 consecutive edges, right? So hopefully that makes it clear that how you're grouping. So the grouping portion, how you're grouping, that is taken care of by the dynamic programming part after you split it. And where you're splitting it, that is the logic that why 3 splits are enough to compute it, right? So absolute min max, this problem is very simple. This is the entire statement. Uh, uh, Subarray is, so we are talking about contiguous subsequences. It just means a subarray. A subarray is valid if maximum element minus minimum element is the same as the greatest element minus the smallest element. Wait, I said the same thing twice. Sorry. The maximum element minus the minimum element is equal to the right element and the left element. Okay, so right and left just means the rightmost and the leftmost elements. So there's no confusion. Yeah. So we just have to count the number of such fruitful subarrays, right? So let's just look at the constraints. Okay, the constraints are like 2.5 into 10 to the power 5. That's pretty high. The array values are also up to 10 to the power 9. Right. So the array values are up to 10 to the power 9. Okay. So what can we do here? So when I see this problem, so what are the observations that I can make right now? So let's say a subarray is fruitful. Okay. So so our array was in actuality a lot larger. Let's say something like this, and this portion was the subarray. So I'll just draw a kind of a graph. The y-axis of the graph basically means the value of the array, and the x-axis means the index, kind of. So it usually helps me think as to the values, what the values are, and so on, right? So it just means that this value is basically the value at this index, right? So what is the right hand side of the equation? The right hand side is max minus min, right? So the right hand side of the equation is basically this difference minus this difference. And what is the left hand side? The left hand side is effectively this minus this. Right minus left, right? I mean rightmost minus leftmost. I mean their absolute values. Okay, so one thing is guaranteed. I mean, it's very obvious, but the right value or the left value cannot really exceed max value or cannot be lesser than minimum value, right? Now, what a subarray is only fruitful when this lower purple line and this lower yellow line kind of like overlap, and when this upper yellow line and this upper purple line kind of overlap, right? Hopefully, yep. So that is kind of so from just the picture we can kind of make that as a like ascertain that something. Right. So what is kind of an improved diagram of an actual subarray, actual good subarray from this observation that we made? It is something like one of like the left and the right ones will be the minimum and the maximum values. So either the left side is the minimum, the right side is the maximum, or the right side is the maximum, the right side is the minimum, the left side is the maximum. So it will be this, or it will be like the inverse, like in an inverted image of this. Okay. You can prove this for like in a better way if you can want to. I think it's given in the editorial as well. But yeah, so this is kind of how you can make this observation just by making a drawing, right? So this is why this drawing this mountains are kind of helpful sometimes, right? So we have already simplified our problem a lot. We now know that we want to count all such subarrays where the okay. So let's make another observation here. Counting this and counting this is kind of similar, right? Yeah. So what are we trying to do? We are trying to count the number of subarrays such that the left element is the minimum one and the rightmost element is the maximum one. So basically all subarrays of this type. This is, as I said, it looks very similar, and what we can do is just reverse the array and make the same algorithm run through the array, right? I mean, it's just the symmetrical and opposite case. So reversing an array and just making the same function run over the array makes sense. Now, what is the thing that like what is something that kind of jumps out here is kind of simple to calculate edge case. What if all the elements were same? Then it would have been covered in both this iteration and this iteration. So what we effectively do is we are overcounting these ranges, right, where all the values are same. So we count all such possible ranges and subtract it from the answer once at the end. Okay. So our reduced problem is count number of subarrays where left index is the lowest and the rightmost index is the highest. Let's see how we can do that. Okay. So let's draw some more mountains. So I'll represent the array in this fashion. So I'm not drawing the boxes right now. Let's just say that so this is kind of a number part of the number line where ith x equal to I has a certain value. That is the value of ARR of I. And then, as we said, it will be some mountains of these sorts, right? Um, yeah. Something like this. Okay. So what is a good subarray from here? So this is a good subarray, I guess. Okay, like just at this peak, this is a good subarray. Um, this is also a good subarray. Uh, this subarray is not good, correct? So all the others are not good, and yeah, these are good. The others are not good. Which are let's look at some examples of which subarrays are not good. Just to clarify. So this black subarray is not good. This black one is not good. Uh, this one is not good. This one is not good. So why I am doing this is the following. There are multiple types of not goodness in some sense. So why are these two subarrays in particular not good? That's because there is an element that is lower than the element that we had fixed our left index on. Okay, so even before, yeah. Okay, so right, why is this not good? I mean, again, same reason, there is something that is lower than the left index. And then there are the second type of subarrays, which are these positions. Why are these positions not good? Well, there is a value that is greater than it to the left of it, like in the range that we are considering, kind of, right? So what is one observation that we can make is, okay, so even before that observation, let me say how we kind of generally approach such problems. Whenever we want to count something of the sort of like counting subarrays with some properties, with satisfying some conditions, the most common approach that we usually take is fix a left index or fix a right index and see which all left indexes or right indexes are valid for that fixed index. So for example, here what I want to do is I'll fix the left index and I'll try to calculate how many right indexes are valid for this left index. So let's call this the count. We will basically add up all the counts for all the left indexes and that will give us the total answer, right? Uh, just one second. Someone is asking, is there any mathematical derivation for escape one? Yes. So it can be reduced to like it can be reduced to another problem, but so what I'll do is, so the escape problem, you cannot take two things consecutive and you have to kind of group them together. The mathematical proof is a bit difficult. I can give you similar problems. So let me check. Right. So this problem is kind of, I mean, it might not look exactly the same as the one in the lunchtime problem, but it's kind of similar but harder. The lunchtime problem was much easier. This is a bit harder. Um, yeah, so here you actually have like, I mean, read the problem, and the proof is something like, so the proof for that problem is, I think, given here. So here, if you see here, I'll give you this link. I'll share this for everyone, sorry. Yeah. So in this problem, if you go to this problem called backup, there is a brief solution mentioned here for backup. That is again very similar to that GOI candies problem up here. It's very similar to this problem. There's a slight difference, but yeah, so the APIO link actually contains a brief editorial sketch for it. For very mathematical proofs, I can just say that the proof for this one is based on, I think, alternating paths on bipartite graphs. Like, it's a bit complicated, but yeah, so the CodeChef problem is much easier. I think you can prove it much simpler using such induction logic or something. So like such a greedy logic is kind of the proof that you need. So yeah, so these are kind of the harder versions. So hopefully, like, just go over them, try to solve it. Yeah. But again, just note that even though the problems might be similar, they are harder. The CodeChef problem is a bit easier. But if you can prove those problems, the CodeChef problem is kind of a subset of them. So, yeah. Sorry, I got way off track. So what were we talking about? I'll just reiterate once more. So what we are trying to do here is, for every left index, we are trying to come up with which all right indexes are valid for that particular left index. So what we do is, so what are some observations again that we can make? First thing that should be kind of like you can see from such a diagram is, once the value kind of so say you are moving the right pointer, so you have kind of so you have a right pointer like this, correct, and you are kind of moving it to the right, correct, and you are trying to see for which all positions this right pointer is valid for the left pointer. So you are, so let's say I am drawing a line from, let me draw a line like this. This is basically the value that is here at the value that is at the left index, okay? And it's not changing for some reason. Anyway, forget the color. So you are kind of moving towards the right, correct? So one thing to note is, once you move past a point which has a lesser value than that yellow horizontal line, that means for everything that is to the right of it, the minimum value will be this portion, right? My leftmost value will not be the minimum anymore. So however much I move this to the right, it will always be invalid, correct? Because my left index is not the minimum anymore. So one quick thing that we can see from here is, we are only bothered about those right indexes which fall in this range between the left index and the first element to the right that is greater than the left index, correct? So how do we find these next greater element? It's a very classic problem. Just Google finding next greater element using stack. I mean, it's one of the basic applications of stack. Hopefully it's well known, right? So yeah, so this is one reduction that we can make kind of on the right indexes. So how does this help us? We now don't need to worry about the left index being the minimum, right? But there's another constraint. that the right index has to be the maximum till that point, correct? We kind of want to solve it in a similar fashion. What we want to do is for a right index to be the maximum till like the left, like from the left index here, the right index has to be the maximum in this range. Another way that we can kind of think about it is, what is the greatest element to the left of this index, okay, that is greater than that particular index, okay? So let's say so it's becoming a bit cluttered. Let's say for this, the greater element is this one, right? For this index, the greatest element to the left is this one. Similarly, for this index, the greatest element is again this one. For this element, I mean greatest element, this is the greatest element, so don't bother. Uh, for all the other elements, even for this, the greatest element is just way too high. Correct. So what can you kind of observe from the picture itself? It's that only those elements whose greatest element is left of the line that I've drawn over the left index, only those elements are valid, right? And if you think about it in this way, the right index value is the maximum till now from the left index, because their greatest element to the left is again to the left of my left index, so they are not in my present range. And if it was not so, that means the maximum, I was not the maximum, the current right pointer was not the maximum. So those are kind of the two conditions that we need to handle. So what are the conditions? Let me just write them down. So let's say we fix left index, capital L, correct? Now count all uh, right indexes are such that what are the two conditions? R is less than next lesser of L, correct? So next lesser of I equal to next lesser element of next lesser element, rather next lesser of I equal to J, such that ERR of J lesser than ERR of I and J greater than I. And similarly, Prev greater is kind of defined as like it should be intuitive enough. ARR of J greater than ARR of I and I greater than J. Stuff like this. So I want to count all indexes R such that R is less than next lesser of J and L is greater than next greater of R. Okay. If we can count all such indexes, we are done. Now, right. So what is kind of the most direct way of using some black box? So obviously whenever we are trying to compute such things, we want to take like use some data structure to compute them, right? I mean, it's not really possible to algorithmically compute all of them very fast. I mean, just using simple stacks and arrays. So we are looking at some sort of a data structure. So what is a possible data structure that could have handled these? Okay, so possible data structure is which needs to support these kind of operations, like basically a query, find all, let's say, points x comma y uh, such that what to say, y is greater than some value, let's say p, and x lies within, and like some L lesser than equal to x less than equal to R. Did I say it correctly? Yeah. So rather y is less than p, I think. So if we had a certain data structure which could answer these queries, where you can like insert points in the data structure like this, and it could compute this type of a query, what you could have done is you convert all these conditions into points. What sort of points? Well, you convert them into points like prev greater of I, comma I. You convert them into these points, and note that you only want to check for, so whatever you effectively doing here, you were doing here that I is, so L less than equal to I, rather here we have named it as R, but let's call it I. So L less than equal to I less than equal to this one, correct? And next greater of I was less than L. Does this look familiar with what query we are trying to answer using the data structure? Well, it's the same thing, right? If we stored points like this, and we could query them, query the data structure for all such points, maintaining these conditions, then we are done, right? So this can be actually efficiently done using merge sort trees. They can even be done like, if you really want to do it, if you really want to code and the stuff, they can be usually done with the persistent segment trees, stuff like that. But these are all online solutions. So a problem can have an online solution and an offline solution. So online in the sense that you are querying the data structure at the moment and then getting your answer back at the moment. If you want to like go over more of how like this intuition that you are trying to convert them into 2D points, where every point has some constraint lying into it, and there is some like how to tackle these problems using merge sort tree persistence. I will link 2 blogs like there. I have talked about a couple of examples here because it's not really that well covered, at least in tutorials and such. So just go over them if you want. So they kind of cover these kind of things, like how to kind of formulate problems in the form of 2D points, and the queries become kind of rectangles in your 2D plane and stuff like that. So like they are a common way of approaching problems. But in this case, what we can actually do is we don't need to have such a data structure, because we can do something called offline processing. So offline processing is, we know what all queries we will eventually kind of need to make, and we arrange the data after we get the queries such that we can make a linear pass and keep a simpler data structure that has less conditions. So what are we effectively trying to do is, we are trying to simplify, like take care of one of these conditions before calling the data structure. Like before we are calling the data structure, we want to say that, okay, I have already ensured that this condition is true. Now find my data structure which only says that is this condition true or not. So how do we do this in this problem? Well, you can generate all such prev greater of I comma I pairs, like in the beginning of the in the pre-processing step, correct? After you have got all these processings, so now like all these pairs, now what you can do is you can make a simple 2-pointer algorithm. Let's say you have a data structure which supports this query very fast. So what is the query? So query is, let's say L less than equal to X less than equal to R. Just count all the X such that L less than equal to X, X less than equal to greater than L and less than R. We will give L and R as the query variables, and you can insert data, like insert some things and make these queries. So these are just simple segment trees, right? These are the basic form of range sum point update segment trees. So let's say you have these at your disposal. So you can even use a Fenwick tree bit sort of a thing. It doesn't matter what data structure you use, as long as you can support this query. Now what do? How do you offline process to make your life simpler? What we are trying to do is, we are trying to handle this constraint on our own. So this constraint y less than p is basically next greater than I is less than L. So what we do is, when we are processing a certain L, okay, so we go from left to right one by one. When we come at a certain L, I want to ensure that I have included all such pairs, okay, into my data structure. So when I say I am including a pair in my data structure, I mean that I am setting, let's say, the pos of I plus plus. Okay, we are not doing anything with next greater of I at the moment. In the data structure, we will only update I. So if we have a segment tree, we will have seg tree dot update. The position will be I and the value will be +1, something like this. So we are saying that when I'm processing a certain L, I have already taken care of all such points such that prev greater of I is less than L. Okay, so if I say that this is true and my data structure can handle this query, so which is effectively L less than equal to I less than equal to R, that means I am effectively taking care of both the conditions together, right? My data structure is handling one of the conditions. I myself, during the like linear scan, I am taking care of the other condition. So how do we ensure that this condition is all well and true? I mean, we cannot just hope that we will just process and it will be true, right? So what we do is, um, so okay, so one question is coordinate compression would be needed, right, for segment tree, as AI is less than equal to 10. We are not using the value of AI. Nowhere have we used the value of AI here. We are only using the value of next greater or next lesser. So all of them will be certain indexes, right? They are indexed as J. We are not using ARR of J or ARR of I anywhere. So compression would not be needed. Right. So let's say we have ensured that till L we have got everything. Now what for L plus 1? How do I update that? Well, just go over all. You have a list of these, right? You keep them sorted according to prev greater of I. Now you just include everything, every point that had the first X coordinate, like the first point, like first of the pair was L. Okay, so this is effectively the same as saying prev greater of I is equal to L. So for all the pairs where prev greater than I equal to L, include them into your segment tree again. Okay, and then like it's kind of a two-pointer. You have this all these points sorted by prev greater of I. As you are kind of doing the scan, you are also inserting the relevant I values such that prev greater of I is less than L. And then your this condition is also satisfied, and this condition is taken care of by the segment tree itself, or like the Fenwick tree bit, whatever. So this was enough to give you the full solution, like the full points. Even I think merge sort tree and everything pass, like should have passed or will pass or something like. I mean, I'm not sure. The editorialist code does implement merge sort tree. Let me go over the tester code for this because it was easier. So Taranfrit's code uses merge sort tree. If you are not familiar with how to implement merge sort tree, do go over it. So let me just go over this code. Oops. Complete. Right. So this is just reading the input and solving. Let's go into the solve function. So here, answer plus equal to solve. So solve is effectively counts all the subarrays. Then you reverse the array, count everything again. So this takes care of both the cases where left is the minimum, right is maximum, or left is maximum, right is minimum. And then you kind of just subtract all the overcounted subarrays, which are basically all the elements are the same. Okay. Now the thing of interest is the solve function, right? So note that how here there is a some data structure. Here it's been implemented using FinVictory, but it can be any data structure. So the thing about data structures usually in this optimization problems is don't think about the data structures and how you will implement it at first. There are some data structures that you will like kind of intuitively figure out which are usually possible, which are usually not possible. And then they are kind of the black box things. Like you just assume that, okay, this can be done fast enough. If it can be done fast enough, how do I proceed? And then you go back to thinking about the data structure. Sometimes it will happen that that thing that you can do fast enough cannot actually be done, but then it's more of a data structure problem than an algorithmic problem. So, I mean, this is again just how I usually think about it, right? So here what it's doing is just computing the next greater and next lesser elements. So this is the next lesser element, I guess. It's computing from the right to left. This is computing from left to right. This is computing the previous greater element. This is the next lesser element. Okay? So this is kind of next lesser, and this is prev greater. So what am I, so in how I explained, we had not been updating anything while computing the prev greater, right? So what is this thing? So this basically means that for all the values which are the greatest in the prefix, I update them then and there because they will be updated anyhow, right? It's not like I will need to include something in my prev greater thing and then it will be updated. Like for them, the prev greater is -1 in some sense. So let's just update it at the first only. That's why if st.empty, then just update them. Else you just kind of store the prev greater thing. So li is kind of prev greater. Okay. And then in the algorithm, like it's really simple for all the, so for every index, for every I, so here what L of I denotes is, so L of I is basically all I such that prev greater I comma I was valid, like was there. Okay. So this is kind of what Li denotes. So when you are at a certain I, you kind of want to include all the things that were prev greater was like possible here. So you include them, you update your answer with I comma next -1, right? You don't want to go to next of I because that is lower than i's value. And then you set, so here it's processing from left to right, hence it's setting some of the stuff to -1. If you go from right to left, you set it to +1. That's just an implementation detail. So yeah, so that was the whole solution. So any doubts, any queries? If not, then I guess this is it then.